So I'm going to talk about this topic, which sounds pretty technical, but I'm going to explain each of these terms and also our result. And this work is actually done in collaboration between the Regner Research Center, where I'm based at, and at the Technical University of Budapest, where Gergely, Bunth, Gábor, Maróti, and Milán, Mosonyi is based. And also Gábor is here, so he can help me with the questions, perhaps. And okay, so what is this topic about? What do I mean by super-exponential distinguishability of correlated quantum states? So I have to come back to one of the most basic tasks in quantum information theory, which have been talked about in this workshop a lot, which is actually the simple binary IID state discrimination. So the question is that we are given n identical copies of a quantum state, rho tensor n or sigma tensor n. Our null hypothesis is that it's rho tensor n, and the alternative hypothesis is sigma tensor n. And then we can perform a measurement on this state, either rho tensor n or sigma tensor n, and depending on the measurement outcome, which could be a 0 or a 1, with a generalized POVM measurement, we will decide that we accept the null hypothesis if the outcome is 0, and we accept the alternative if the outcome is 1, and then we want to actually find the best POVM with respect that we don't make big errors. So what are the errors? These are the usual type 1 and type 2 errors. The type 1 error is that although the null hypothesis is true, we actually reject it, so we get actually 1 as a measurement outcome, and we say that it was sigma tensor n, and then yeah, the null hypothesis is true, and we get 1. So this means that actually, although the state was rho tensor n, actually with some probability we get the probability, we get the outcome 1. But we could also have the other type of error, that actually the state was actually, we say that the state was, we accept the null hypothesis. When it's false, actually it should be sigma tensor n and Tn, these two errors. Okay? And we have learned from many talks yesterday that actually the best achievable asymptotics for these errors, if the states are not trivially related to each other, meaning that the supports of rho and sigma are orthogonal, so if they are not that trivial states, then actually the errors decrease exponentially to 0. And then there are a lot of work done what this exponential decay, this constant, the exponential is. I mean, there are several famous theorems. One is the quantum Chernoff bound, which says that if you take the symmetric setting, that you look at both errors symmetrically, and you look actually the scaling of both these errors, the same exponential scaling. Actually, what you get is some minimum of an expression which is related to the Rényi divergence between those two states. And then there is the asymmetric setting, where the result is given by the quantum Stein's lemma, the simple quantum Stein's lemma, not the generalized one, where actually what you say is that you don't want that the type 1 error should decay exponentially. You just say that it should be below an epsilon, and then you say that you look at the infimum of like the best decay of the type 2 errors, and then you take epsilon smaller and smaller, and it turns out then the exponent of beta is actually given by the relative entropy between rho and sigma. And of course, there are these famous trade-off relations where you can see if you want to look at different type of exponential behaviors in the errors which are allowed, and they are given by this trade-off is given by the Höfting bounds. Okay, this is all nice and fine, but this is like the simple setting, and this has been known for a long time. But of course, one can go beyond this simple setting. One way of going beyond the simple setting is to look at composite state discrimination. So maybe you have several states and you want to do like a multi-discrimination, or maybe you want to do a binary discrimination, but you have, let's say, a single row tensor n state and actually a couple of lots of states. So like that you are promised that I'm either having row tensor n or some states from a big set. And for example, you have heard yesterday talk about this and about also some more generalized questions concerning this possible generalization of the quantum Stein lemma that I mentioned. But there is also another way of making more general statements, or which is, I think, very interesting and studied somewhat, but not that much, then when we don't do IID state discrimination, but correlated state. So this will be the talk. Okay, and so what is our setting exactly when I say that we do correlated state discrimination? So now, instead of having like, if we go back here to this picture, having a lot of rows here and a lot of sigmas, and we can do a POEM, we actually take two spin chains, say infinite spin chains, and two states on those two infinite spin chains, which are correlated. And usually we also assume translation invariance, because if you don't assume that, then many things can happen which are not so interesting, but more or less trivial in some sense. But if you take, let's say, translation invariant states on infinite spin chains, then we can ask that if we are allowed to measure on a region of n consecutive sites, let's say qubits or qubits, then we can decide whether we were in the state omega 0 or in omega 1 in this infinite spin chain. Okay, and then we also want to study the error asymptotics here. And okay, actually people have done this. And of course the generic question when people have studied this were the following thing. In the correlated scenario, can the error asymptotic be qualitatively different than for the IID case? Or if it's not different, how can you calculate out these exponential exponents? And if it can be qualitatively different, then is it for very weird states, or is it also for in physically interesting states? Does it happen that you have something very different from the IID case? Let's say for non-equilibrium steady states, or for Gibbs states, or for ground states of local Hamiltonians. We will study these questions, and there has been some previous studies. For example, for local Hamiltonians, if you take Gibbs states or thermal states, finite temperature states, there are some nice results, and they show that there is an exponential decrease of errors, like in the IID question. Then there has been actually many similar results for various set of states, on some states on the Carr algebra, or on CCR algebras, or on non-equilibrium steady states. But in all of those cases, they observe this exponential separation in the discrimination of two states, like exponential decrease of the errors. Okay, and our question was whether we can go beyond this. And actually, our idea was like, what's going wrong there? Why don't we see anything more interesting? And one idea that popped up, which I will also come back later, was that, okay, what do we usually in quantum physics say? That if you have a phase transition, then on one side of the critical point and on the other, like the state changes very much, so maybe they are very different. However, if it's still not the critical, so that was our maybe first guess, that look at two different sides of a critical point, but they usually have a finite correlation length, so maybe even better would be have a finite length, interaction length Hamiltonian, which have several different critical points, and look at different critical points of that. And that's actually what we did, what I'm going to present. Or to be more fair, actually in our paper we considered a very general scenario of certain fermionic quasi-free states that we transformed to the spin chain. They didn't even need to be ground states of a Hamiltonian, didn't even need to be pure. They had a certain condition. It could be also a mixed state. And we gave some results on these. But in this talk, I'm not going to mention this except if there are some questions. And I will only consider examples coming from many-body physics. And the examples that I'm going to mention is actually a really simple system, 1D chain and the 1D XY chain. Okay? And for this system, actually we know where the critical points are. And there is a lot of critical points, so this is great for us. First of all, if H is equal to 1, like the magnetic transverse magnetic field, and then gamma is between -1 and 1, then when you look at the thermodynamic limit, it will be a critical point, and if you go from H smaller than, let's say, 1 to bigger than 1, then there is a phase transition. Similarly for H -1. And also, if you put gamma equal to 0 or 1, we looked at actually it's 0 in the end, but we can also look at the 1 case. Then there is also a phase transition for a variety of ages, actually for the 0 case. Okay, and the theorem that we arrived to in this context was the following. We said that if we would have the ground state of this XY chain for the XX case, so when gamma is 0, then if you would take two distinct magnetic field values, which was between -1 and 1, then we could actually not characterize exactly how the best asymptotic goes, the errors, how they decay, like in the fastest way, but we could find POVMs such that the errors actually decayed faster than exponential. So if you would try to think that you take the log of the errors and a -1, so it was not like a minus a constant, but minus C log n. So like the decay was e to the n log n. This we could prove with that the decay of the errors is at least that big. So we could have super exponential distinguishability. And more interestingly, or perhaps not that, it was not that unusual to think that it was actually done only with projective measurements. So you didn't need to do anything fancy with the POVMs. Okay, so that was the main result, and then I'm going to go a little bit deeply to the conclusions and the outlook. So, okay, so basically, what we did? What we showed that for a certain pairs of ground states of local Hamiltonian, super exponential discrimination is possible. Okay. Moreover, we found that the critical ground states of this XY model was like that. But there was also something interesting here, which I didn't mention, that actually you could do binary composite hypothesis testing for this. So interestingly, in this theorem, those projections that would give you these very good asymptotics for the super-exponential asymptotics for the decay of the errors, they could be used, the same projections could be used to distinguish between almost, basically between any of those transverse magnetic fields. So for example, if somebody would say that, is the magnetic field larger, like H0, suppose it's larger than H1, is it larger than H0 and or smaller than H1, we would have the same asymptotics. So in this sense, this also gave us a binary composite hypothesis testing with a super exponential distinguishability of the hypothesis that the transverse magnetic field is above certain threshold versus that it's below strict lower value. Yeah, and And then there is still some things, there is still some things that we haven't clarified yet fully. I mean, first of all, we only prove that it is at least as fast as exponential of minus c n log n, where n is the system size. So it's a super exponential, but like just a bit super exponential. And also, actually, we don't know whether we don't know two things: either that our POVMs are the best POVMs, probably not. The second one is that for our POVMs or the best POVMs, is this actually the real rate, or actually can it decrease faster? And with Gábor and Milán, we are actually investigating this a lot nowadays. And of course, there are also many general questions that you can ask. So in general, if you have a translation invariant state on the infinite spin chain, you could ask whether there is an upper bound on the speed of convergence to 0, or you can converge even if it's translation invariant very fast. And you could ask the same question about ground states of local Hamiltonians. Maybe ground states of local Hamiltonians are special and they have an upper bound. And finally, it would also be very interesting for me, from a many-body perspective, to know whether such super-exponential discrimination is also possible between a critical and a non-critical ground state of a local Hamiltonian. Let's say we could use the XY model, where we have now some critical state and we say non-critical state. I mean, one has a long-range correlation, so we could hope yes. On the other hand, we can also ask a more daring question. What about if there is two non-critical states, where actually there is no long-range decay of correlations? There one might guess that perhaps there we don't get a super-exponential distinguishability, only exponential, but we haven't been able to prove it. So if someone has any idea, maybe come to me. We also have some ideas. So thanks a lot. And I would.
Thanks for a great talk. I'll take questions, and then it's easier if people talk into the microphone, so I'll try and pass it so that way the question is heard. If you are asking a question that is not in the microphone, then maybe Zoltán can repeat it.
Thank you for that talk. It was very interesting. I'm learning a lot about how difficult it is to prepare ground states. And, you know, in this talk, you prepared two ground states. And
right.
I'm wondering, there's a class of local Hamiltonians where the ground states, preparation of the ground states is trivial. I'm wondering if you've checked if the transverse field XY model that you're using falls into this class of easy to prepare ground states, or is this one of the Hamiltonians that's kind of stuck in the QMA complete of really difficult preparation of ground states?
So first of all, I mean, it's no, it's not difficult to prepare. To prepare it exactly needs depth. If you have n qubits, depth n, length n, to prepare it approximately, you can get away with log n circuit. And of course, there is a prefactor in front of the log n, which grows while you make it better and better. So I would not say these are hard to prepare states.
Thank you.
So thank you for nice talk. So can you obtain the constant C as an exact form?
Okay, that's a great question. And actually, during QIP, actually Milán wrote to me whether we can do that. First of all, we would need to see whether this is really the asymptotics. Gábor, you have some numerics about this, which shows.
We don't know yet.
Okay. So we don't know yet. But I agree that if we can say something about that, our next goal will be, this is actually what we are talking about, somehow do some clever tricks to perhaps do some type of Stein lemma, or Höfding bounds even, for that
So
thing.
do you have an idea about the informational meaning of the constancies, like relative entropy or
Exactly. So this is what we are hoping for. Okay. I mean, maybe I'm telling some secrets here. So what we are hoping for that we should sort of like look at the relative entropy of between bigger and bigger regions and then rescale it and something like that. But we are not done with this research.
No, thank you so much. Thanks.
Any further questions?
Hey, thanks for the great talk. So just to be clear, so like you don't have any general upper bound, right? So you don't know whether there could exist models for which the decay is like e to the n squared minus n squared or something like this.
We don't know. So it would be great to have an understanding of generic, let's say, ground states of local Hamiltonians to fix it. Let's say translation invariant local Hamiltonians, even in 1D. We don't have. This is the only example where we could do something. And
thanks a lot.
Yeah.
Other questions? Are there other kind of intuitions about other kinds of systems where you might look for such a thing of the super-exponential scaling? Is it besides phase transition, say, or?
No. I have to admit, no. Actually, when I'm telling you this, it's also not completely true. As I told you, there are some non-equilibrium steady states that has been studied earlier, and they got exponential decay of the errors. But I think there are certain non-equilibrium steady states I'm trying to engineer such that where we use the similar tricks that we could get here to get a super exponential. That would be maybe the thing that I still have an idea, but otherwise I don't have an idea where it could happen. But I mean, you can see that for thermal states it doesn't happen. So I mean, then what are the interesting states then? I mean, thermal states, non-equilibrium steady states, ground states, sort of.
Sorry, probably missed the point. How the measurement looks like in this TN?
Great question. That was the key of this thing. And maybe I revealed that it was like not that hard to do it, although we spent a lot of time. So basically, these systems can be translated into free fermionic chains, so like in the car algebra, on the fermion chain, a free fermionic chain, and basically they can be diagonalized by the Fourier transform, the infinite Fourier transform, and how we built the measurements is roughly, but this is just roughly, that we took a finite chain and we took Fourier transformed creation and annihilation operators and built some projections from them and did it and did that. That was them.
Okay, before we thank Zoltán, just to say that the next talk will start on the hour, and because it's quite noisy with the chairs, if people can just make sure that they're sitting down by the hour. But there's a 5-minute break now if people want to go to another session. So thanks very much, Zoltán, again.
Thank you.